All right, so next we're going to look at how the musical instruments produce music. And there are two types of musical instruments we're going to see. There are string instruments generating standing waves on a string, pretty much similar to what we um, studied in chapter 15. And then we can have also wind instruments that can also generate standing waves, but using the air molecules, so basically vibrating air columns. All right, so in terms of then the type of the type of vibration we can have, you can say, right, you can create a vibration by plucking, striking, bowing, and blowing. So those are the type of uh, sources of waves, right, or vibration that we can have. And then vibration can be transmitted through a string if it's a string instrument, or wind if it's a wind instrument. So these are some of the let's say a table with in terms of frequencies, right, for let's say frequencies for octave beginning with middle C. So if you're a music person, you probably have used these notes, and maybe even know the frequency that they specific frequency they represent. But here's the table for sort of like your information. If there's an example that you need to reference, you can always look at it. So you have C is 262 hertz, C sharp is, let's say, 277, and F is 349, and so on and so forth. So those are basically when you play an instrument, right? So you use those notes, and every note has a different frequency. That's why the sound, sounds the way it is. In terms of then what we're going to look at, not necessarily kind of like instruments and specific type of notes, but most of, like, let's say, is the physics behind that. So we're going to look at in terms of, let's say, this standing waves on a string that we looked at last chapter. We can model it for the, let's say, a guitar or a violin, thing like that, some kind of string instrument. So we know that whenever the string is vibrating, right, you can have then different harmonics. So you can have first harmonic or the fundamental, then the second harmonic, third harmonic, and each time to go from one harmonics to another one, right, we have very specific frequency. You can't just have some random frequency to go from a first harmonic to second harmonic. Remember, so once you have your equation for the first harmonic, F1, which is generally equals to NV, well, assuming that N is equals to 1 over here. So it's 1 over 2L times V, because what we have here is the wavelength related to the length of the string. So where lambda n is equals to 2L over n. So then we can use this general equation to always, let's say, relate the wavelength that you see for specific harmonics to the length of the string. So you can see, right, if it's lambda 1, that means the first harmonic. So it's equals to 2L divided by 1, so 2L, which means that this shape is only, half of the wave. So that's why in this length L, you see only half of the wavelength. But when you go from first harmonic to second harmonic, then you can see that the length of the string can generate the entire wave itself. So that's why L is equals to lambda. And that means, once you find the frequency for your fundamental, then any subsequent frequencies will be then n times, that means the next harmonic, times F1, the fundamental. So if, let's say, fifth harmonic will be 5 times fundamental, and so on and so forth. So basically, that's what we learned in previous chapter. Now, if you're a music person, then you can also learn about overtones. So the overtone is, in a way, of the sort of like, let's say, the standing wave that comes after the fundamental. So that you have first fundamental, but the first overtone is basically what comes after the fundamental. So that's why the second harmonic is the first overtone, third harmonic is the second overtone, and so on and so forth. So in a way, this n, you can relate this to the number of antinodes or number of harmonics. And the antinode is basically always one less. That means the second harmonic is the first overtone, and thing like that. So you can see that in terms of for the standing waves, right, generated on a guitar, so you can use your fingers to make the string shorter and longer. That means you can technically control the length or the active part of the length of the string. Because yeah, you're not necessarily changing the length of the string. What you're changing here is which part of the string is actually, oscillating, vibrating. So, and what it does here is just basically, we know that if you change the length of the string, since frequency is equals to 1 over 2L times V, or thing like this, right? So something like that. Then doing that, well, if you change the L, you're changing frequency. Same with the lambda, right? It's 2L over N. You're changing the length, you're changing the wavelength. So those are the things. That means, you can technically uh, use this technique to, affect the L directly. All right. So sometimes, the sound that produced by the let's say the string, if you're, let's say, trying, to play that for a big audience, right, in let's say in a lecture hall or something like that, well, you might want to, like, let's say, amplify, right? That means, increase the loudness. And a lot of times we do have sort of, like, let's say, analog amplifiers, or let's say digital amplifiers, depending on, let's say, if let's say here you have a digital, right? So basically, um, creating electrical, let's say, signature of your mechanical vibration, and then, it travels through those wires, and then when it reaches the speaker, and then it converts back. So then basically converts to a mechanical sound, and then, let's say it exits the speakers. um, so that means what we have here is we're basically creating what we call resonances. So the resonant is basically when you can have the sound become amplified. Generally, you can think of, like, every sound has a frequency, right? So, let's say specific frequency, and then you can, amplify that by creating this resonant frequencies, find this correct resonant frequencies where the sound can actually be amplified. All right, so here's then next is the wind instruments. So then with the wind instruments, we're going to see that they come in two different types. So let's say on the left side is a flute, right? It's basically open on both sides. So it's called open tube. So it's open, so open at both ends. And then you have, for example, a clarinet, which is open only at one end. And that's, called, closed tube, or, open closed tube. So for the flute, it's open here and open over there, and the for clarinet is open here. So one thing that we will see here is when we're looking at the standing wave generated by the, wind instruments, right, in air column. So we can have those two different scenarios. So let's say there's going to be open, or open closed, but, you can also have closed, right? But in terms of, like, let's say if you have a musical instruments, you want to have either open, or, open close. You don't want close. Like, sound has to escape somehow. All right, so here's then what we have. So these are modeled by, for the, let's say, like, flute instrument, where it's open at both ends. So we're going to look at what we call, instead of open, we're going to say just open tube, open at both ends. So we can call this like an open tube. So what we have here is, you can see, right, there are two different, let's say, diagrams. That's because we can do it in terms of displacement of air, and in terms of, like, pressure variation, like we already discussed in the previous lecture. That means we can have exactly same thing described by two different waves, in terms of pressure waves, or in terms of, like, displacement of air. And the difference between them here is this: when you're talking about the displacement of air, so let's look at this left side. Displacement of air always requires there to be an antinode where you have the open end. So let's say here's an opening over there, it has to be an antinode. Here's an opening, there has to be an antinode. So that means antinode, and then you have one node. So that means you have two antinodes and one node. For the same thing, if you're talking about pressure variation, where there's an open end, has to be a node. So a node and a node. That means exactly the reverse. So for displacement of air, two antinodes, one node. For the pressure variation, two nodes, one antinode. Okay, but still what you get here is basically first harmonic, or the fundamental, where again, L is equals to 1/2 times lambda. That means you still have exactly the same thing as a standing wave on a string. So lambda n is equals to 2L over n, and then frequency f of n is equals to n times v over 2L. Those two equations can also be used for the uh, open tubes, right? Or the tube that is open at both ends. Okay, so going from the first fundamental to second fundamental, the difference here is, you can see, right, it has now two nodes. So for this particular case, right, when you talk about displacement of air for the open tube, the number of harmonics is basically equal to the number of nodes that you have. So first harmonic, one node. Second harmonic, two nodes. Third harmonic, three nodes. So then, and so on and so forth. Again, also you can talk about overtones, where overtones are the pretty much shapes or the standing waves after the fundamental. So the first overtone is the second harmonic. All right, so same thing you can see over here. This is, let's say, the pressure variation in air for the open. So you have a node, and a node, and just two antinodes. And in a way, you can see that if you're talking about then the pressure variation, this is very similar to the string, the shapes that you see, right? To the, standing waves on a string. So this is exactly how the, standing waves, if you go back over here, see, this is exactly how the first harmonic looks like if you have a string standing wave, second harmonic and third harmonic. So the shapes for the pressure variation in air for the open tube pretty much looks exactly like that. Okay. And again, those are the two equations that we're using. If you have a tube with one end as closed, then what you have here is this. So again, two different ways, displacement of air and then the pressure variation in air, and exactly same differences again. If it's an open end, there has to be an antinode for displacement of air. If it's an open end, there has to be a node for a pressure variation in air. So, but still, what you have here is, this is first harmonic, second harmonic, third harmonic, and you can see sort of like, let's say, how the shape progresses, right? So you have one extra segment here and two extra segments over there, and same thing here, like going from here to there, you adding another full segment, here adding full two segments, and thing like that. Now the difference here is this. When you're considering this, a tube with closed at one end, first harmonic or the fundamental ends up being lambda n is equals to then 4L over n. Not 2L over n, but 4L over n. Because when you see this shape, this is only quarter of a wave compared to here when this is half of the wave. So this is half of the wave. So for the first harmonic, you have half of the wave in that length L. But here you have only quarter of the wave. So that's why for the first harmonic in the length that is given to you, you only generate quarter of the wave. So then you have this equation for the wavelength. Then the frequency n is equals to n times v over 4L by replacing, a wavelength in this equation. So you get this. So this is for the this is for the f of n equation. Then you can see, right, when n is 1, here's the equation for the fundamental frequency. Now, the next one, when you talk about then the next harmonic, what you get here is this. When we go from a fundamental fundamental frequency or first harmonic to the next one, what we see here is the next one is the third harmonic rather than the second harmonic. And then after that is the fifth harmonic rather than the fourth harmonic. That means what we have here is when I have this equation, lambda n is equals to 4L over n. N is 1, 3, 5, 7, and dot, dot, dot. So that means only the odd harmonics are present in a closed tube. Okay, so the overtones and harmonics, right, basically only come in odd numbers. 1, let's say 3, 5, 7, and so for the overtones. Okay, that's because the way that we have for this closed one end tubes, there is no way for the air to create those waves with 2, 4, 6 harmonics. Okay, because there has to be requirement, right, at one end to be a, let's say, an antinode, the other end to be a node, so it does not generate the even number harmonics. That means you only have for this particular, let's say, configuration, you have odd number of harmonics, 1, 3, 5, 7, and so on and so forth. Right, so that's basically the important, right, the biggest difference between open open and closed. And then when you have basically closed, it's pretty much similar to the um, same as open tube. That means you have pretty much same equations over there. Only when it's closed at one end, then you end up with this kind of like unique equation set and unique sets that only only allowed to have. You're not not allowed to have even number of harmonics. All right, let's look at an example here. We have a 1.2-meter long pipe is stopped at one end. Near the open end, there is a loudspeaker that is driven by an audio oscillator whose frequency can be varied from 10 to 5,000 hertz. Neglect any end corrections. What is the lowest frequency of the oscillator that will produce resonance within the tube? All right, so let's look at this part over here. Okay, so we're given the length, which is 1.2-meter long pipe. That means we can say that L is equals to 1.2 meters. And then we're given basically our, the frequency range, right? So 10 to 500, basically it's, driven by an oscillator, goes from 10 to 500 hertz. And we want to find for part A, the lowest frequency. Okay, so to find the lowest frequency, well, we have this equation. F of n is equals to since it's stopped at one end, means it's basically closed at one end. So it's equals to n times v over 4L. Okay, so we have this equation. Well, the lowest frequency will be f of 1, which means that 1 over 4L times v. Okay, now what is v? Well, we're talking about sound, speed of sound, right? So it's a it's a pipe, and we're talking about the sound waves. That means it is just basically 343 meters per second. So 343 meters per second for the speed of sound, then 4 times then the length, 1.2 meter, long pipe. Calculate this, we're gonna get 70.5 hertz. So that's basically the lowest frequency that we can have. This is for the fundamental frequency for this particular loudspeaker. So loudspeaker, it generates sound waves. Part B, it says, what is the highest frequency that this will produce? Okay, so now, one thing we can see is this. Here's the fundamental, 71.5. And it's within this range, so we're fine with that. If I calculated and I got 7 hertz, for example, that that means the fundamental would have been less than, allowed, let's say, the range. So, maybe you got something wrong or something like that. So, but here we got the number that basically within the range that we want. The next is, let's say, what is the highest frequency that we can have? All right, so the highest frequency, you want to look at then in terms of something that, close to 5,000, but doesn't go beyond 5,000. Okay, we don't know if it's exactly 5,000. So this basically this, it can vary up to this, from 10 to 5,000. All right, so let's see what we have. We know that equation for the higher harmonics is f of n is equals to n times f of 1. Okay. Now, what I have here is that the n is equals to 1, 3, 5, because of its open closed tube. Okay. So now, our goal here is to find what is this highest n highest end, where we can have kind of like this 5,000 as our roof frequency. That means this is equals to 5,000 divided by 71.5 hertz. So 5,000 hertz over this, units cancel out, and we get 69. When we calculate this ratio, we get 69. So then that means we can go all the way to a 69th harmonic. That means f of 69 is equals to 69 times the fundamental. So 69 times 71.5 hertz. So here we get 4,930 hertz. Okay. All right, so this is basically what we got, 4,930 hertz. Part C then it's asking how many different frequencies of the oscillator will produce a resonance. Okay, remember, so then what we have here is the 69 hertz, sorry, not 69, 69 is basically our odd harmonics, right? So this, when you calculate this, these are the odd harmonics. So odd harmonics higher than the fundamental frequency. So then what we do, we just divide this by 2 roughly to get then 35 as the number for the allowed resonance frequency. So that's a total number of resonance frequency if you divide 69 divided by 2. Because remember, so there's even odd, but when you talk about, like, let's say open closed, so you are only allowed the odd numbers, so you take that number and divide by 2 to get the ones that are allowed harmonics. I mean the resonances, sorry. All right, so here's another example. So we have a measuring the frequency of a tuning fork. So we have a simple apparatus for demonstrating resonance in an air column is shown in this diagram. That's actually something we have used in one of some of our physics labs as well. A vertical pipe is open at both ends, is partially submerged in water. So this is basically, oops, sorry. So this is our pipe, and it's open at both ends. So at the top there's basically you have it's open to air. At the bottom part is basically submerged in water. All right, so and the tuning fork vibrating at an unknown frequency is placed near the top of the pipe. So the length L of the air column can be adjusted by moving the pipe vertically. That means one thing we have here is you can say, right, this is basically the level of water. Okay. So this is something that we learned from the fluids chapter, which is basically in physics 37. When you have two containers that are connected, like over here, their water level is exactly the same. So you can say, right, while you submerge, the water level in this pipe is exactly the same as water level, in this container. That means what we can do here is, as we, let's say, take the pipe and submerge even more or less, then we can controlling how much water level we have. That means we can change this L. Okay. Because as we change this L, then we are basically changing where the closed part of this pipe is. Because let's say here's the pipe. So when there's a water, then this acts like a barrier. So it's basically like a wall. So when I move it up or down, so let's say if I submerge even more, then I'm technically, let's say, changing the length where the sound can travel and reflect it back. So let's say, all right, so that means the sound waves generated by the fork are reinforced when L corresponds to one of the resonance frequencies of the pipe. Okay. So for a certain pipe, the smallest value of L for which a peak occurs in the sound intensity is 9 centimeters. Okay. Generally, what we have here is when you reach that resonance frequency, the sound is amplified. That means, if you, let's say, strike the fork, this tuning fork, with the mallet and put it next to the open end, then the sound is going to travel down hit the water, and reflect back. And if you find the right length, then the sound can actually be amplified when it hits this, let's say the water barrier. Because what you're doing once you find that correct length, you generating, let's say, this standing wave like that, right? So you're generating the correct standing wave, and you then get the resonance frequency. Okay, now what we have here is says for a certain pipe, the smallest value of L for which peak occurs in the sound intensity is 9 centimeters. What is the frequency of the tuning fork? All right, so that means, let's say whenever this 9 centimeter is, let's say achieved, that means the length between the open end and the water is 9 centimeters. Okay. Then what you get your first resonance. Okay. And it's kind of hard to draw it here, but it should look like this. It should look like that. So that's the first resonance. Okay. And when you have that, then you can say that f of 1 is equals to 1 over 2L then times the velocity. Well, 1 over 2 times, well, 0.09 meters, because that's what our L is, then times V. Well, that's 343 meters per second because it's a tuning fork generating the sound wave. If I calculate the frequency, I should get 953 hertz. That means for the first harmonic, the sound oscillates at 953 hertz. That means this tuning fork has a frequency of 953 hertz because once you hit it with the mallet and put it next to the open end, the sound has the same frequency as the tuning fork. Right. Well, here's the image actually for that, which you can see. This is how the first resonance looks like. What are the values of L for the next two resonance conditions? That means, one thing we can do, you can lower the water level. As you lower the water level, you're increasing L and allowing another, shape to be formed. Putting even, lowering down the water level even more allows another shape to be formed, another resonance to be formed. That means we can look at it in terms of then that. All right, so one thing we have here is there are a couple of ways you can do that. You can find frequencies. So remember, so you can use this equation. F of n is equals to n times f of 1. Find, let's say, f2, and say that this is equals to 2v over 4l, and then solve for l. Then find f of 3, then say it's 3v over 4l, and then solve for l. Or we can look at it in terms of this. We can find the wavelength for the fundamental, which is velocity over the frequency, 343 meters per second over 953 hertz. So we get 0.360 meters. That's the lambda 1, which means the wavelength for the first resonance. Then we know that from the equation that I showed you, right, wavelength lambda n is equals to 4L over n, where n is equals to 1, 3, 5, dot, dot, dot. That means we already have lambda 1. The next would be lambda 3 and n equals 3 and n equals 5. So if I rearrange, I can say, all right, so then from here, the L, let's say, will be equals to, if we're talking about 3 over here, right? Then we can say that this is equals to 3 lambda over 4. Okay. So 3 lambda over 4. And so this is, L for 3, and L for 5 will be then 5 lambda over 4. Where basically this becomes 3/4 of the fundamental, basically the lambda 1. So which is 0.3 So this is going to give us 0.27 meters. And then this will be 5/4 of the 0.36, and that will give us 0.45 meters. So that's how we can find then, the L for the next two resonance conditions. That means we start when it's 0.36, 0.27, 0.45, and so on and so forth. That's basically, let's say, 0.27 below this level over here. Okay, so this one we get, let's say below, relative to the, the top, the top of the tube, and then you go down 0.27, you have one, 0.45, you have another one, and so on and so forth. All right, here's what we have about quality of sound, noise, and superposition. So for example, it says, why does a trumpet sound different from a flute? Well, remember those overtones? Oops, those overtones, right? So the overtones means that you have, when you play a tone using some kind of music instrument, when you play a note, what it does, it doesn't just give you one frequency. It gives you the fundamental on all the harmonics, all of them together at the same time. So then when you're looking at the, let's say, the superposition, which is all the, those harmonics combined together, that's why one music instrument sounds completely different from another one, even when they're playing exactly same note. Again, because once you start play one note, all the harmonics together simultaneously are played. You can see this from this diagram over here. So this is clarinet. Oops, sorry. Here's clarinet, piano, and violin. Okay. So what we do here is when you play a note, look at how all those exactly same time occurred. All of those in harmonics. Same with the piano. Same with the violin. Okay. So all those, overtones, if you want to, harmonics or overtones, all of them play together. Okay. So that's why even though if they're exactly same note, well, you get completely different sound, right? Completely different loudness because of the, let's say, the sounds that you hear is the superposition of all those harmonics combined together, and it looks completely different, which you can see from here from the graph, right? Depending on what type of instrument that you have. So that's why, let's say if it's a middle C played on clarinet, violin, and piano, well, you're not going to be able to, let's say, confuse one with another one because they have completely different, loudness, completely different sound because of, with what that's what we call sort of like a quality of sound or noise, right? That's why, because of, those overtones. All right. So next we're going to talk about this interference of sound. And this is something we already looked at also in previous lecture. This is when you have two waves that overlapping. So you can see, right? So here you have speaker A and here you have speaker B. And what they do here is each one, when, oscillates, generates a sound wave that propagates as a sort of like a sphere in spherical, let's say, geometry. So this is for the, let's say A. So A propagates like this, for example. And then the other one is, so this is then basically, I don't know why it keeps happening. All right. So then this is basically speaker B. And you can see, right, here those two overlap. Here those two overlap. Here those two overlap. And wherever they are overlapping like that, they generate constructive interference. Okay, so they generate constructive interference. So right here, you can see, right, this is speaker B. At that, it's a crest of speaker B, but this is between the crest of the speaker A, and that actually is a destructive interference. So you have constructive, you have destructive, depending which part of the shape you're talking about. So again, so this would be a constructive because you have crest of one overlapping with the crest of the other one. Here, crest of A overlaps basically with the trough of B, because if this is a crest of a crest of B, here's the next crest of B. Exactly in the middle of that is the trough of B. So here, then you have crest of A overlapping with the trough of B, and that's a distractive interference. All right, so you can also look at it from here. So if you choose some point C, what we have here is this is the sound that is coming from speaker A. Gets to the point C, then this is the sound that comes from the speaker B, gets to that point C. And if at point C they have crest with crest or trough with trough, then you get constructive. But if you have at that point, some another point where those two waves get to that point, and you can see, right, it's crest of one with a trough of the other one, not crest on crest, trough or trough, but crest with another trough, then this is then distractive. So technically, if it's an open field, you stand right there, you hear no sound. Those two sounds cancel each other. Okay, so that's what we can have with the constructive and destructive. And you can see, right, the difference is, in a way, is if I take this to be RA and this to be RB, which is the path length, so wave B is, has this extra distance that it has to travel. So sometimes we call this delta R, which is RB minus RA in this case. And that's the, that path length difference between those two waves, that extra distance that it has to travel. Now, if that extra distance is equals to, let's say if I divide it by lambda, if that extra distance is equal to some kind of integer number, then it's a constructive interference. If that equals to some kind of fraction, then it's a destructive interference. So let's say if I get 1 or 2 or 3, or like let's say 0, right? So like let's say 0, 1, 2, 3, then it's a constructive interference. If I do delta R divided by lambda and I get, let's say, 1.5, or well, we start with 0.5 or 1.5 or 2.5, that means a fraction, then it's going to be a destructive interference. That means the path length difference, which you can see, right, it's half a wavelength or 1.5 wavelength or 2.5 wavelength. So when it gets there, there is a difference between crest and a trough. That means you have a crest with a trough, not the crest with a crest or a trough with a trough. And that pretty much destroys the sound. So here you can also see, in terms of another phenomenon we call like Beats frequency, is when you have two waves that have different frequencies, and at some point, if they're both traveling, let's say, to the right, because one has a higher frequency than the other one, let's say if they start with the crest and crest together, at some point you can see, right, this, let's say this red is moving faster because it has a higher frequency, same wavelength but higher frequency, but still speed is equals to wavelength times frequency, one with the higher frequency traveling faster. So at some point, then you have crest, blue crest, which was with the red crest before, now is overlapping with the trough of the red. So you have then destructive interference right here, constructive interference right there. And this represents their superposition. When they are constructively interfering, you get the maximum amplitude. When they're destructively interfering, you get zero amplitude. So again, because the blue is moving faster, at some point it overcomes, and then again you have a crest and crest. So another constructive, but then eventually again another trough, another destructive. So what you get here is sort of like, let's say this is beat frequency. So constructive, destructive, constructive, destructive, and so on and so forth. So that's basically what we call beat frequency. Okay. Now, for the interference of two waves, again, if we consider two waves moving in the same direction with the same amplitude and same phase, but with different frequencies, we can find the beat frequency by, adding those two waves together, right? So A sine omega t kx minus omega t plus phi for one, and exactly the same thing for the second one, add together, and then this is then the equation for the beat frequency. Okay, so this represents a wave vibrating at the average frequency with an envelope at the different of the frequencies. So kind of like it goes like this, right? It goes like this, but what you have here is that it's kind of like goes like this, goes like this, goes like this. So it changes, from between constructive and destructive interference. Okay, so let's look at an example here. Sound source A is located at x equals 0, y equals 0, and sound source B is located at x equals 0, y equals 2.4 meters. Okay. The two sources radiate coherently and in phase, and an observer at x equals 15 meters, y equals 0, notes that as he takes a few steps from y equals 0 in either plus or minus y direction, the sound intensity diminishes. What is the lowest frequency and the next to the lowest frequency of the source that can account for this observation? So let's see what we have here. We can start with, you know, doing a diagram. So here's my diagram. The y-axis is x-axis. And what I have here is x equals 0, y equals 0. That's one speaker. So right here, that's one source. Let's call this source 1. X equals 0, y equals 2.4. Well, let's say 1, 2, somewhere over here is then the second one, source 2. Okay. That's source 1 and source 2. And then it says the observer at x equals 15 meters, y equals 0. So let's say somewhere over here. Okay. Observer right here, standing, notes that if moving either plus y, that means like let's say in this direction, plus y or minus y, the sound intensity diminishes. Okay, now we can then assume that compared to moving up or down, right, plus y minus y, because it diminishes, that the position that the observer is right now at that x equals 15 meter, y equals 0, is in a position of a constructive interference, right? And it's moving parallel to the line through the source, right? So you can see, right, the source is on the y-axis, so it's kind of moving parallel to the source source axis, which both of them on the y-axis. That means one thing like we can do here is I can draw the like this, right? So then the distance from one, let's say this will be, let's call this R1, and then another one which will be R2. So that's sort of like a distance from source 1 to this point P, let's call it point P, and then source 2 to that point P. Okay. So R1 is simple enough, right? It's 15 meters. R2 here is then square root of 15 meters square plus 2.4 meters square. So because this is 2.4, this is 15, right? We have to find R2. All right, so let's say we get 50. All right, so then R2 is 15.2 meters. All right, so next what we do here is this. So because it's a constructive, then I can say delta R is equals to n times lambda. Okay. So for destructive, then it would have been delta R is equals to n plus 1/2 times lambda. So this equation is used for the constructive interference. This one is for the destructive interference. Now, we know that it's a constructive interference, so we go with this equation, delta R equals n times lambda. Okay. Now, delta R is then the difference between those two. So then delta R is equals to 15.2 meters minus 15 meters. So this will give us 0.2 meters, and it's equals to then n times lambda. Now, one thing I have here is I can use this to solve sort of like, let's say, so I can say lambda is equals to 0.2 over n. And then remember, so I need the lowest frequency. So then remembering that V is equals to wavelength times frequency, I can say then frequency is equals to V over wavelength. So which then will give me 343 meters per second, where wavelength is zero point 0.2 over n, or this will be, so this is n times 343 divided by 0.2, which then gives me, roughly speaking, 2000 n. It's kind of rounded to like, sort of like a nearest thousand. So 2000 n. That means this is f of n, and it equals to 2000 times n. That means the first one, f of 1, will be 2000 times n is equals to 1. So 2 kilohertz will be then the first one. Then the second one, second lowest, will be f of 2, which will be then 2 times 2000. So that will be 4 kilohertz. And then those are my two lowest frequencies, 2000, 4000. Then it will be, you can see the pattern, right? 6000, 8000, and so on and so forth. All right, so next concept that we have here is the Doppler effect, which happens when the source, where, some kind of source that has maybe like, let's say, moving relative to some kind of observer that has ability to move as it generating this vibration. So let's say you have a siren on a fire truck, and as the siren generates the sound, which is moving at the speed of sound, let's say the source itself is also moving. It means the fire truck is moving. And when the fire truck is moving, then if you're an observer, the sound frequency will appear to be different if the source, the truck, is moving toward you compared to when it's moving away from you, or even compared to when it's not moving at all. So for example, if there's a siren here at 200 hertz, if the source, which is the truck is at rest, Vs equals 0, velocity of the source equals 0, the frequency for the observer that the observer will hear will also be 200 hertz. If the source, which is the truck, moving toward the observer or away from the observer, this frequency that will be measured by the observer will be different. And it will be different depending if it's moving toward or away. So let's say both of those observers, so let's say f of prime, so they will hear 200 hertz if the source is at rest relative to them. Because, all the source is at rest, and they both hear exactly the same frequency as the siren. But as the truck starts moving, you can see, right, what happens here is that the crest, which is the wavelength that the siren generates, starts compressing because the source is moving in the direction of the wave. Which means if the wavelength decreases, you can see, right, the frequency is equals to velocity over wavelength. So when wavelength decreases for the observer toward whom the track is moving, so then the frequency will appear to be increasing. For the observer behind the source, for the source that is moving away from the observer, the wavelength will start to be increasing. And again, frequency of this observer prime is equals to V over wavelength prime, let's say. Well, now the wavelength increases, which means the frequency will be then decreasing. So that's kind of what we have. So here, wavelength is decreasing, so the frequency is increasing. Here, wavelength is decreasing, so the frequency, sorry, other way around. So here's the wavelength increasing, so the frequency decreasing. So that's why, depending on which, if the source is moving or in which direction it is moving, this apparent frequency, right, apparent pitch sound or the frequency will change. This is known as a Doppler effect. The Doppler effect is when the source of the sound is moving relative to some kind of observer. Well, technically, you can have observer moving toward the sound or away from the sound. You will still have the same Doppler effect applied. Okay. So as I mentioned, right? So this is basically based on the fact that since wavelength is changing, then so is the frequency, because we always assume that speed is constant. Speed doesn't change. So if the wavelength it changes, that means automatically frequency must change. Okay. So then what we have is this. The change in frequency is given by this. F of prime is equals to F1 minus V source over V sound. So this is velocity, this is speed of sound, this is speed of source. Okay. If the source is moving away from the absorber, then you have positive inside compared to the negative if it's moving toward. So this is moving toward, this is moving away. Okay, so this is moving away. So that's why what you have here is that this plus minus help you to get higher or lower frequency depending if it's moving away or moving toward. Okay. So you can also have the absorber, right, moving relative to the sound. So that means it's the source. So you can have a source at rest and the absorber is moving toward the source or away from the source. In a way, same idea can be applied. It just mathematics becomes a little bit, different. So we have new set of equations that we can use for the moving absorber. So in this case, the F prime, which is the apparent frequency, is equals to 1 plus V absorber over V sound times the original frequency. And if absorber is moving away, then F prime is equals to 1 minus V absorber divided by V sound times the original frequency. Again, one thing you will see is that frequency will change depending if it's the absorber now moving toward or away from it. Very similar, let's say Doppler effect applied here. All right, what if you have both absorber moving and the source is moving? That means, let's say they're moving toward each other or they're moving away from each other. Or maybe, let's say, the absorber moving to the right and source is moving to the right, but let's say one is moving faster than the other one. In any case, combining both of those equations, you can have then one equation that takes into account basically everything. So it's more general equation. So then F of prime, which is the apparent frequency, equals the original frequency. Then here we have V sound, speed of sound, plus V absorber. This is plus if the absorber moving toward. And then V sound minus V source. So think like this. This equation, if moving toward each other. That means, for example, if the source is 0, then this is 0. And then you basically have this equation right here. But if the absorber is 0, then you have basically equation when the source is moving toward the absorber, with absorber having, 0 velocity. That means this is basically can be used for the moving toward each other. You can think like this. Either absorber is moving toward the source or source is moving toward the absorber, or they're both moving toward each other. Then F prime is equals to F, then V sound minus V absorber divided by V sound plus V source. So this is if moving away from each other, or one of them moving from another one and things like that. So this is basically for the moving away from one another. Okay. So then you kind of have to be sort of like, let's say, mindful in terms of what type of scenarios do you have. That means this is plus every time absorber is moving toward the source, regardless if the source is moving toward or moving away, or if the source is at rest. That means as long as the absorber moving toward the source, that's positive over there. If the absorber moving away from the source, then it's negative over there. Okay. Same thing is here. If the source is moving toward the absorber, it's always negative there. And if the source is moving toward the absorber, this is positive over here. That means, again, regardless what's the state of the absorber is the absorber moving toward, moving away, and things like that. So that's kind of what you have. If the source is moving away from the absorber, that should be positive over there. Okay. All right, so let's look at an example. So you have a physics professor demonstrates the Doppler effect by tying a 600 hertz sound generator to a 1 meter long rope and whirling it around her head in a horizontal circle at 100 RPM. What are the highest and lowest frequencies heard by a student in a classroom? Okay. Now, what you have here is, so let's say if this is the observer, let's say this is the observer, here's a teacher. So let's say here's the string. So what she does, it kind of goes like this. So away towards, sort of like it kind of goes back and forth. So that's why, let's say when it's moving from here to there, it's toward the observer. From here to there, it's moving away from the observer. So that means we can look at it in terms of, being able to hear the different frequencies when it's moving toward and away. All right. So one thing we have here is this little of, extra things here. We have then sort of like a frequency, which is 600 hertz, which we then can use to find the angular frequency, which is 600 hertz